Okay, so today we're going to continue the EM waves that we started, Maxwell's equations and EM waves. And we're going to finish it today, and so that next week we're going to start ray optics. So today we're going to finish electromagnetic waves. So remember where we started. We started with Maxwell's equations in differential form. We said del dot E, and we assumed that there are no charges or currents. And so the right side here, it's rho over epsilon naught, but there is no charge. So this part was 0, and we said the divergence of B is, this one is 0. The curl of E is equal to minus dB dt, and the curl of B was mu naught J, but there is no current, so J is 0, so we get mu naught epsilon naught dE d. So those are the 4 equations. If you find a solution, it has to satisfy all 4 equations simultaneously. Okay. Then,
Professor,
yes.
do we say there is no current because we are in space, or?
Yeah, we're somewhere where there is no current.
Okay.
Yeah. Then we also mentioned that, just to remind us that the wave equation has this form. If you find a function that looks like this, second derivative with respect to x is equal to 1 over b squared, second derivative of f with respect to time, then you know you have a wave equation, and this is the speed of that wave. And we also use the following form. We said if you have a vector field, then the curl of the curl of f is equal to the gradient of the divergence of f minus the del squared or Laplacian of f. Okay. So we used this equation. So, and then we went from there. Okay. So let's do this curl of curl and then go from there just quickly. So the curl of E is this. So let's do this. The curl E is equal to minus dB dt. And we said, okay, this is equal. And why are these equal? Because it's one of Maxwell's equations, right? And then we said, okay, let's do the curl of this. I'm going through this quick because we did it last time. So this is just a quick review. So this is simply the gradient of the divergence of E minus the gradient squared of E equals to, next we can take the time derivative and then the curl, or we can take the curl and then the time derivative. So we write this minus d dt of the curl of B. Okay. Now the divergence of E is 0. Divergence of E is 0. So this term dropped, and on the left side we had minus this squared equals to a minus sign and a minus sign, they both go away, and we just have d dt of the curl of B. But the curl of B, according to the 4th equation, is this mu naught epsilon naught, the time derivative of E. Okay, and so we get square root of E is equal to mu naught epsilon naught, and then the time derivative of time derivative would be the second time derivative of E. So this equation here. We also did the same thing, but to this equation, right? We did the same thing, but to this equation, and we got, I would just write the result. It was exactly the same thing, but instead of E, you have B. Okay, so these two equations. Then we said, okay, let's look for a solution to Maxwell's equations, one solution that is not zero. And we proposed a particular solution, and we're going to just check whether that solution, if it's a solution, it has to satisfy all of Maxwell's equations, okay? So it's a good exercise to go over that. So we said a possible solution to Maxwell's equations is the following. We said it's this E, it's J hat, or let me write the J hat in front, just EY, or E naught sine of kx minus omega t J hat, and then B equals to B naught sine of kx minus omega times t k hat. We said this is a possible solution, and if someone says verify that this is a solution to Maxwell's equations, how would you verify that? What would you do? If I tell you, let's say this, I give you a polynomial, right? X squared plus 3x cubed minus 7x, all right? And I say equal to 0, and let's say I say 7 is a solution. How would you check if 7 is a solution?
Plug it in.
Yeah, plug it in. So that's exactly what you do. So you plug it in and see if it's a solution, if it actually works, okay? So what you do is do the divergence of E and see if it's equal to 0. Divergence of B and see if it's equal to 0. The curl of E if it's equal to the time derivative of B, and this one also, okay? So let's do that, okay? Because I see some, last time there was something mysterious people didn't understand. What does it mean? How do we do the divergence? So it's a good time to review it. So let's see. So we're going to check, okay? So our goal is to check if these two are solution to that. If they are, they have to satisfy all the equations at the same time. So the divergence of V, let's see what we get. Okay, first, what does it mean to do the divergence? It looks like this. Partial of x I hat plus partial of y j hat plus the derivative with respect to z k hat dot product with E. What's E? E is this. E naught sine of kx minus omega t j hat. All right? Let's see if this gives us the desired result. What's the desired result? What do we want this to be? 0. We'd like it to be 0. So let's check if it is 0. Let's do the first one. The dot product of the first term with this term. So what's the dot product of I hat with j hat? 0. Good. Next one. What's the dot product of j hat with j hat? That's 1. So it's not 0 yet, but there is this derivative with respect to y that we also have to do. What's the derivative with respect to y of something that doesn't depend on y? That's 0. Next one is the final one, is this one. K hat dot j hat is 0. So they're all 0, either because of the dot product or because the derivative is 0. So 0. So this first equation does satisfy, or this electric field does satisfy the first equation. Second one, we need to check if the magnetic field satisfies this equation? Well, you have to do just exactly what I did, and then you will find that it is equal to 0. Should I do it, or you will do it on your own? It's exactly the same step. Right, skip it? Okay, let's skip that. So you can verify yourself that if you do the divergence of B, and you will get 0, but using this. Okay, so you can do that on your own. Next one, let's do this one. The curl of E. So the curl of E. So I'm going to first do the curl of E because it's kind of log. So I'll do the curl of E, and then I will take the time derivative of B and then set them equal. Okay, that's what I'm going to do. I will do first, devote my attention to the left side and then to the right side. Okay, so let's do it. Curl of E. So curl means this. It would be exactly the same thing, but here there will be a cross product. So you have this d dx I hat plus d dy j hat plus So first, let's do the cross product of the first term with this term. I hat crossed with j hat is k hat, right? I hat crossed with j hat is k hat. And then we have to take the derivative. d dx of this, what does it become? You will get what? Yeah, the derivative with respect to x will bring a k outward, and then it becomes a cosine. Yes, so it becomes k, and then e naught. Let me write it actually as e naught times k times the cosine of kx minus omega times t. And then we said it's in the k hat direction, right? Because the cross product I hat and j hat is equal to 0. Next one is the cross product of this term with this. J hat cross j hat is 0. Yeah, so that one is 0, nothing. Now the next one, first the k hat cross j hat is not 0. The k hat cross j hat is minus I hat, no problem. But what's the derivative with respect to z of this function that does not depend on z?
0.
0. So only this term survives. That's the curl of E. Now let's do the time derivative of z, time derivative of b. Here is b. Let's take its derivative with respect to time. When you do the derivative, it becomes a cosine, right? And then minus omega comes out. But there is a minus sign waiting. So it becomes overall plus. Yeah, so no minus sign. So it just becomes this. B naught omega cosine of k x minus omega times t, and it's in the k hat direction. It's in the k hat direction. You see, this one had to be in the k hat direction because let's say we chose it to be in the I hat direction. Could these two be equal? No, this one is in the k hat. This one, if they are equal, they have to point in the same direction. Okay, so it is possibility. So let's set them equal to each other and see what we get. If you set them equal, this one has a k hat and this one has a k hat, and this one has the cosine and this one has that same cosine. So it means this part and this part have to be equal, right? For them to be equal, this part needs to equal to this part. Yes? So we get E naught times k equals to B naught times omega, and that means E naught, it means E naught equal to omega over k times B naught, and I think we do remember what omega over k was. What was omega over k? 1 over speed or speed?
It's V.
It's the speed. It's the speed of the wave, and what speed did they move? We said last time was the speed of light, right? So, c, the speed of light, and this is, by the way, this is the wave equation, right? That's the wave equation. All right, so let's box this one. Any questions on this? So let's summarize what we know. Notice the electric field, it has a y component. It's in the y direction. But it moves, the wave itself propagates in the x direction. So let's say here's the y direction. So the electric field looks like this, but the motion is in the x direction. That's the x direction. The magnetic field has a z component. Let's say the z component is this way. So the magnetic field is doing this. It's moving in the x direction, the wave, but at any time the magnetic field points either in the plus or minus k hat direction. Okay. So the electric field and magnetic field are perpendicular to each other, aren't they? Okay? They're perpendicular to each other, and both of them are perpendicular to the direction of motion. Right? The wave moves in the x direction, electric field is in the y direction, and the magnetic field is in the k hat direction. So they're perpendicular to each other. So let's summarize all of this stuff. So we know this, the following summary of what we saw. Number one, the electric field is perpendicular to the magnetic field. E is perpendicular to B. Right? This means perpendicular. Electric field is perpendicular to the magnetic field, which is to say that the electric field dot product with the magnetic field is equal to what? If they're perpendicular? 0. Right, that's what it means. Number two, E and B are perpendicular to the direction of motion. Both E and B are perpendicular Number three, the direction of motion, the direction of propagation, is the same as what? Well, what is j hat cross k hat? What's the cross product of j hat and k hat? Negative I or plus I? Positive I hat. So the cross product of A and B, which this one is j hat, this one is k hat, is the same, is in the same direction as the direction of propagation. So the direction of propagation is the same as E cross B. Okay? It's the same. I'm not saying it's equal to it, but it's in the same direction. It's the same direction. Number four, the speed of propagation is c squared equals to 1 over epsilon naught mu naught, or c, I should say. That's the speed, c. And it's about 3 times 10 to the 8. Okay. 3 times 10 to the 8. finally, or number 5, E naught is equal to C times B naught. E naught is equal to C times B naught. Okay? E naught is the amplitude of the electric field, right? That's the maximum value for the electric field. And B naught is the maximum value for the magnetic field. So the electric field and magnetic field's amplitudes are related. They're not independent of each other, they're related. E naught is equal to B naught times the speed of the wave, speed of propagation. Let me show you, there's a little bit of algebra I want to get ready. So this one here, C is equal to 1 over epsilon naught mu naught. That means, of course, C squared is 1 over mu naught epsilon naught, right? Which means 1 over mu naught is equal to epsilon naught C squared. Do you see that? 1 over mu naught is that. On the other hand, if I want, on the other hand, 1 over epsilon naught is equal to mu naught C squared, which means epsilon naught is equal to 1 over mu naught times C squared. I would need this a little bit. Just to get some visual, the direction of the electric and magnetic fields in this particular case. So here is the x direction, here is the y direction, and the z direction is sticking out, it's coming towards us. The electric field has a y component, so it looks like this. Okay. This is the electric field. In this case, the wave is propagating in this direction. It propagates in that direction at speed c, right? This is the electric field. Electric field. The magnetic field is in the z direction. This is the magnetic field. I'm probably not going to do the best job, but there are better pictures in the book. Okay, this is the magnetic field. It's also propagating in the x direction at speed c, and so let me put, this is b. It's the magnetic field. That doesn't look good, actually, after I looked at it. But you got the idea, right? Okay. All right. Now, it's time to discuss the energy of an electromagnetic wave. Energy. How much energy does it carry? And then, finally, how much momentum does it carry? Now, the energy will be in the same direction as the electromagnetic wave, right? If the electromagnetic wave is coming towards you, the energy is directed that way, towards it. So let's recall the following: energy density, I think we do remember the energy density. It's the energy per unit of volume, and it has the symbol UE. This is for the electric field. Okay. So the energy density, the electric field, it was 1/2 epsilon naught E squared. The energy density in the magnetic field is 1/2, actually 1 over 2 mu naught B squared. That's the energy density in the magnetic field. This is the energy density in the electric field. To be specific, for the case, so let me write here. If E is equal to E naught sine of kx minus omega t, j hat, and B equals to B naught sine of kx minus omega t, k hat, then the energy density, the one with the electric field, UE, will be 1/2 of epsilon naught E naught squared sine squared of kx minus omega times t. And the one with the magnetic field will be is equal to 1/2 u naught B naught squared sine squared kx minus omega times t. Any questions so far? Well, the total energy density, which is U, and it's UE plus UB, will equal to the sum of these, right? The sum of these. There is a half, so we can factor the 1/2. Let's see what's left. Will be epsilon naught E naught squared. And then 1/mu naught B naught squared. And then we can factor the sine squared of kx minus omega t. Okay. That's the energy density, energy per unit of volume. It's energy per unit of volume. Next, I would like to know how much energy there is given off per second per unit of area. So we find per second and then per unit of area, or per second per unit of area. The energy per unit of time is known as power, right? Energy given per unit of time is power, and so that's what I'm going to find in a second. Give you time to get this. So we'll imagine still our wave is propagating to the right in the x direction, that way. By the way, there is nothing special about the x direction. It could be in the y direction or the z direction. We have these two solutions give us a wave that's traveling in the x direction. We can combine them with other solutions that have the wave propagating in the z direction, and then other solutions that have the wave propagating in the y direction, and then combine all these, and then you have a wave that can be traveling in like 3 dimensions, as a like radiating away. So you can combine them. You can add solutions, because the sum of two solutions is also a solution, because the functions are those differential equations, they're linear. Okay. So imagine our waves are traveling to the right. Let's take a box. So let's say here's a box. Of area A. This is the side area of the box. The side is area A. And I wait for a time delta t. So the width of the box is delta x. And delta x, how fast is the wave traveling? Speed of light, c. So if I wait a time delta t, it will travel the speed times time, and that will be my delta x, right? That would be my delta x. what is the volume of this box? What's the volume of a box? The area times the width, right? Or the depth. So the volume of the box, delta V for volume, is just the area times delta X, and that is area, and then C times delta T, that's the volume. So how much energy is within this volume? Well, I can take the energy density and multiply it by the volume. That gives me the total energy within that volume. Is that clear? Energy density means energy per what?
Volume?
Per volume, yeah, it's joules per cubic meter. So if I want the energy, delta U, it would be the energy density times delta V. So we get delta U would equal to little u times delta V, which is the area, times C times delta T. Okay? C times delta T. Let's divide both sides by delta T. I get delta U over delta T. That's the energy per unit of time. What is that? Power. So power. So we get power. I will write the word power. Is U times A times C. Next, we want power over area. So the power over area would be, well, divide both sides by area. What do we get? Just U times C, right? U times C. This power over area has a special name. It's called S. And then the average of that is the intensity. Intensity is the average power per unit of area. So this has the symbol S, okay? Has the symbol S, and I'm going to write what S is in a second.
What was little u?
Little u is all this stuff. This whole
Okay,
thing.
alright. And
Yeah.
then big U is just.
Big U is the energy.
Right.
This is the energy per unit of volume, this is just the energy. Yeah. So let's write what S is. Here's S. And now S has a name. Okay, I will tell you what the name is. It is UC, right? U times C. So I'm going to write it here, put it there. So I have this. It will be U times C, so I'll put here 1/2, and then I have C, and then epsilon naught, E naught squared, plus 1 over U naught, B naught squared, sine squared of kx minus omega times t. We will do some work on the side a little bit, and so let's see what the work on the, some side work to just figure what this is. Okay. It turns out that 1 over mu naught B naught squared is equal to epsilon naught E naught squared. Okay. Meaning the amount of energy carried per unit of volume in the magnetic field is equal to that of the electric field. They have equal portions of energy. So let's do some side work. Here's the side work. Let's do it right here. Okay, let's do that side work right here. What is 1 over mu naught B naught squared? Well, it's equal to this. First of all, what is 1 over mu naught? Oh, maybe I should have done the side work here. That's okay, I started there. 1 over mu naught is epsilon naught C squared, right? So 1 over mu naught itself is just epsilon naught C squared. Now what is B naught? B naught is E naught over C. Yeah. So it is E naught over C squared. And you can see when you square this, you get 1 over C squared on the bottom. And then there is C squared on top, so that cancels. And so you just end up with epsilon naught E naught squared. Yes? So you see this and this are equal to each other. So that what I'm saying is the energy density is the same. So what happens if I have epsilon naught E naught squared and then here epsilon naught E naught squared, this one, right? So it becomes twice, right? So twice, so this 1/2 goes away. So we get then S will equal to just epsilon naught, oh, and then C, and then E naught squared, and then sine squared of k x minus omega times t. Again, what does S represent? Power over area, right? Power over area. That's what S is. What we really want in a moment would be the average of this S, the time average. How much is it over a period of time, not the instantaneous one. But in order to find it, to find the average, I'm going to rewrite this as follows. Okay, so I'm going to write this as follows. So this part, the front part, I'm going to write it as follows. We have epsilon naught C, and then E naught squared. You might think it's tedious. Why am I doing it? You will see in a second. There is a reason. It's equal to epsilon naught C, and then E naught, right? E naught. E naught times E naught. Okay, so this is E naught squared. So it's E naught times E naught. One of the E naughts, I'm going to leave it as E naught. The other one, I'm going to write it as C B naught, or C B naught. Yeah. So the other one, I'm going to write as C times B naught. Okay? Is that clear? This is E naught, and this is still E naught, but just written differently. And I would like to have both, the E naught and the B naught, for a reason that you will see. So this becomes C squared, epsilon naught, C squared, E naught, B naught. But epsilon naught is 1 over mu naught C squared. Epsilon naught is 1 over mu naught C squared. So this is 1 over mu naught C squared on the bottom. Yeah. And then I get C squared, that cancels. And then E naught, B naught. And so that's equal to just 1 over mu naught E naught B naught. So in other words, S can also be written as 1 over mu naught and then E naught B naught sine squared of k x minus